morning. Thanks for coming. The weather is pretty bad, so I'm glad some of you could make it. Any questions before we start? Okay. So the goal for today is to finish up our discussion on Knight-Bayes classifier and then move on to a variant of Knight-Bayes called Gaussian discriminant analysis, which is fairly similar to Knight-Bayes classification, except that instead of assuming that the data is a set of binary attributes or binary features, we're going to assume that it's a vector of continuous value. Right? So we'll see how that works. All right. So, but before that, let's go back to Knight-Bayes, right? So you remember that the basic code idea behind Knight-Bayes classifier is that it assumes independence between different features, right? And because of that assumption, it can factorize or split this joint probability. Because if you remember, we need to compute what is probability of Y to be malignant given data, and by applying Bayes' rule, it turns out that the main quantity, one of the quantities we need, is this class conditional probability, right? So what is probability of X to be whatever we observe, given that class was malignant? Yeah. And just because of this assumption that all of these features are independent of each other, we can write this expression as simply a product of these individual probabilities, right? So that is the idea. So that is why it turns out that in Knight-Bayes, we don't need to, we only need to learn 2 times D parameters, right? And then the whole thing works, right? So that is the idea. So we don't need too much of data in. So now the next question is, how do we estimate or how do we compute these probabilities, right? And the idea is that we model each one of these distributions as a Bernoulli distribution, because this xj is essentially the value that the jth attribute takes, right? And the jth attribute obviously it just takes 2 values, so it's easy to model it as a Bernoulli random variable, which means that we need to estimate the probability of this Bernoulli, so the parameter of the distribution. So if you remember from our previous discussions, the parameter of a Bernoulli distribution, there's only one parameter, which is theta, which is sort of the probability of getting X, or probability of it being 1, right? So how do we estimate those? And then later we'll also see that we also need the probability, the parameters for Py, because remember we are going to apply the Bayes rule. So there will be this times Py equal to malignant. Now again, Y itself takes 2 values, malignant versus benign, which means that we can model that also as a random variable, as a Bernoulli random variable, and we just need to figure out the parameter of that, right? So if you look at all of these, so you can think of it as that this is our model, Knight-Bayes classifier, and these are all the parameters. So we need a parameter theta, or small lowercase theta, which is for Y. This is for Y, right? So it will tell you, what this will tell us is what is the probability of Y to be 1 and probability of Y to be 0, or benign, malignant and benign. This will be theta of course. Yeah. So we need that. Then we also need for each. So we need theta class 1, comma 1. Theta 1, 2. Theta 1, D. So let's say we have D features. So since each feature value is going to be modeled as a random variable, Bernoulli random variable, we need each one of these, right? And the same way we also need theta 1, 2, 2, 1. So this is for the second class, or the benign class, we can say. Right? So what each one of these will give is, this will give us what is the probability of x1, or x1 to be whatever value x1, and given y is 1, or let's say 1 means malignant and y is malignant. So this will give us that class conditional individual probabilities. Same with this, let's say will give us what is the probability that x2, the second feature, takes certain value, given y is 2, right? Now remember, yes.
So you get two classes. So if we have one that is like 1 and 1
So the question is, what is the relationship between these two, right? So these are two classes. So okay, so that's a good question. Let me just finish one thought, which is, remember that these x1 and x2, they all can take only two values. They can be either 0 or 1 and binary, right? So the question is that, let's say theta 1 1. Theta 1 1 stands for what is the probability that the first feature takes value 1, given class is 1. Right? Because I'm just saying that x1, all of these can only take two values, 1 or 2. They're binary actually. And theta 1, 2, 1 is what is the probability that the first feature takes value 1 given y is 2. Right? Now, what you asked was, can we say is theta 2, 1 simply 1 minus theta 1, 1? Right? That's a good question. So anybody has any thoughts about that? See, think about it this way. These both are not really modeling the same event. This is modeling the event that what is probably x1 is 1, even y is 1. This one is x1 is 1, y is 2. So there are two different events. So they think of these as two different processes or two different points being passed, right? What you might be thinking about is what is the probability x1 is 2, the other value. This of course will be 1 minus theta, right? Because these both are the two possible events that this value will be linked, but these are not related. So that is no. Alright? So these are the parameters that we need to estimate. So how do we estimate it? We estimate it given some training data. And the way to do it, so today we are going to look at how to do it with MLE, which is maximum likelihood estimate. And then later I'll talk about how you can extend it to incorporate priors and so on. So the MLE approach is fairly easy. All you need is to express the likelihood of your data. Right? So what is your data? Our data is just a set of vectors. Training examples. Right. So let's say our data looks like this. There is a training example. This is a vector. This is the first training example, and it's labeled. Second training example, it's labeled. And so on. So this is our training data. And we need to compute the MLE of our data, right? So I'm going to represent this whole big thing with a G. Right? So we need to compute what is the likelihood of G. Likelihood given some data that we know. So I'm using this data to just represent all of these data. Okay? So data is like, it's just a box, there's no part. It contains all of these data that we really need, right? So LD of data will just be a product over I equal to 1 to n. Let's say we have n data points in our training data. And the probabilities of the ith to be xi, comma yi, dy. Right? So this is a joint probability because both of these are identical. So we need to compute a joint probability of each training example and we multiply it and we get a likelihood. And then later we'll take a log likelihood. And that will simply be just a summation log of p. Okay, right? Any questions about it? Alright, so now let's express. Now, what is this probability? This individual probability, that is the mean. This here. So now let's try to figure out what is the probability of the training example to be xi, whatever small xi you observe, and the label to be y, right? So now for this we need to look at our line-based sort of thing. Remember that this depends on this, right? So let's write it as a chain rule. So this will be P yi equal to yi times P xi equal to xi given yi. Right? This we can write because of just the probability chain rule. Right? And then this is where things become interesting. Remember, this is a vector, right? Vector with d values. And because of the 9-phase assumption, we can just write it as a product. So this will actually be P yi equal to yi times product, because we are assuming they're all independent given yi, right? They're conditionally independent, which means this will be j equal to 1 to d. That's in your d attributes. So P, the jth value, to take whatever jth value you observe, given yi. Right? So because we have just split it up. Now let's write these probabilities in terms of the probability distribution, because we know what form they take, right? So probability of yi to be y. Now remember, this yi can either be 1 or 0, right? So we can write that simply as so this will, because this is a Bernoulli random variable, right? So this just will be using theta. Theta raised to yi, 1 minus theta, 1 minus y. Right? Because I'll come to this in a second. But so this is just you making use of the fact that this is a Bernoulli random variable. So this is the probability mass function for a Bernoulli random variable, right? And it's easy to understand. See, yi can take either value 1 or 0. So if it is 1, then it will be theta, with this part will become 0. And then if it is, if yi is 0, then it will be 1 minus theta. So that's just sort of tossing that form. Okay. So that is fine. And then, sometimes I keep jumping around between two values. I assume it takes 2 values 1 minus. Okay. And then the same thing we can do here. So each one of these conditional random variables, right, is a Bernoulli random variable. And so each one of these can be written as times the theta yi. The yi will tell me which class it is, right? So remember we have 2 thetas here, so it's either 1s or 2s, and 1s and 2s are given from the yi. Just driving myself into a right, so I should just use zeros here. This is one set of thetas, second set of thetas, and they're all binary. Right. Times, so this will be raised to power whatever xij is, and 1 minus theta yi, 1 minus xi. Right, so this is basically the core equation to compute the probability, joint probability of these two, of one training example, right? Given that we know these are our theta. So, any questions? Yes. From this step onwards? Yeah. So this part is clear, right? How to compute, how to express the joint probability as a product of these two probabilities, right? Now we need to figure out what are these two, and then this part is also pretty clear because of the 9-phase assumption. This can be written as a product of these two, product of all the different attributes. So remember, xi is going to be a vector. Small xi is actually a vector, which is xi1, xi2, xid. These are the d features that it takes, right? They are all binary. Now, and because we are assuming that each one of them is independent of each other, which means that we can write this joint probability. Because this is a vector, that's why I call it a joint probability. So that can be split up into products of individual probabilities. Right? So this I guess is sort of obvious. Now, what we want to do is we want to express this, because we're computing the light table, right? So we want to express all of these in terms of the data that we have, right? Now, for the yi, because we are modeling that the class label as a random variable, verbally random variable, that means you can express its probability using this expression. That's the PMF of that, right? And here, what we can do is, now if you look at each one of these expressions, so let's take a certain example. Assume I is 1, so it is class 1, right? And j is, so we're looking at the first feature. So what will be probability of x 1 1 equal to x 1 1, given y 1 is something, right? So let's say it's 1. Y. So this is what we have to compute, right? But now remember that we have assumed that each one of them, this is very similar to what I wrote here. This is the same thing as this. The only thing is you see extra subscript here because now we're looking at the ith training example. But it is the same value, right? What is the probability of x11 to take 1 or 0 given one of the classes? Right? And that we have assumed is represented using one of these data, right? So that is why so this one will be just for the first class, for the first attribute, whatever your data is. So in general, you can write it like this. Yij. Right? So, I mean, I would advise when you go back to sort of look at it again, but it's kind of just sort of flowing along because of this assumption and just the fact that we are using all of these parameters, right? So now what happens is, now you can, so this is P. So what we have computed here is the joint probability of one training example. Now you can feed it here, right? And you can compute the log likelihood of your entire data by just putting it there. And what will happen is that I'm going to make a small jump here, but the log likelihood, or just call it LR. LR of our data set, given whatever our data, all the parameters, right, will just be just a summation over all of these values, a log of these values, right? And then when you compute it, it will be the summation I equal to 1 through t n. And then I take a log of this probability. When I take a log of this, it just becomes log of theta yi plus log of 1 minus theta 1 minus yi, right? Plus, and even this thing will just break up into a log. It's a big log under it. So this will be summation j equal to 1 through t log of theta y I j ij plus log of 1 minus theta y I j 1 minus xij, and this summation was made. So this will be the total log likelihood of the data set. I'm just applying log and just replacing the products with the sum of the log, right? So that is what we compute eventually. I can simplify it a little bit because I can bring the yi's here. That will be I equal to 1 through n yi log theta plus 1 minus yi log theta plus something xij So what you see here is an expression that you can actually compute given your training data, right? Because you know all of these values. So these are all of your training example values. And these are data that you don't know. So then what you can do is you can actually use your minimized routine that you use for neural networks, where you can compute this and then compute the derivative with respect to each one of these thetas, and then compute the gradient and feed it to that. But it turns out that you can here actually exactly compute it. So you can exactly set the gradient to 0 and compute that to MNEs. So the next step would be to just simply take this and compute the derivative of this with respect to theta I. So we have multiple parameters, right? We have theta, yi, j's for both class and one feature. So we can compute the derivative with respect to of this LL with respect to these, set it to 0, and you get the answer, right? So what I'm going to skip is just that brief step, because that's just too much notation to write. But if you look at look at the discussion in the handout, it should be very clear, right? But what happens in the end is pretty interesting. So what happens is, if we compute partial derivative of this log likelihood with respect, let's say just that theta parameter that is connected to the y, and that's small theta, and then that will be, if you look here, right? So here there is no theta at all, right? All the theta is over here, that's small theta. That means that when you take a derivative, this will go away, right? So that will just be summation I equal to 1 through n, and then derivative with respect to theta yi log theta plus 1 minus yi log 1 minus theta, right? And the other part will go away, because this will just be 0. It does not depend on theta at all. And then when you compute this, this will be I equal to 1 through n. And then you can do this, right? So it will be and then what we do is we set it to 0. When we set it to 0, what we will get is theta will be just equal to number of times yi I is 1 in the days. And this is very similar to what we did in the coin toss graph, right? So all it is doing is that it is counting the number of times you see 1 in the whole data set, dividing it by the total number of tosses or number of examples, and that is the MAD estimate for theta. Very similar. It's almost assuming that we didn't have x, and y is just a random variable, which is simply a coin toss, right? So this is what will come up. And then if you go through the whole process, what we will see is that even the theta of 1j. So this is the random variable jth associated with the jth feature for the first class, right? So this will just be equal to number of times so n when j will be number of times xj is a jth feature is 1 when yj is when yi is. The number of times in the training data you saw xij to be 1 when the class was 1. Right? So this will be just the expression of that, and everything else will be similar. So data of 0j for the other class, it will be n0j over nj. Number of times you saw this feature to be 1 of when the class was C, right? So this is a little jump from here, but you just need to sort of do this process and it will come up. And I'll show you an example. And an example it seems fairly straightforward. This is just a painful process that I took you along. The reason for that is because maybe here it's fairly obvious, but for other different types of classifiers that you might come up with and look at, the process will be similar. So you need to be aware of how these things are derived, right? So for example, later on it could happen that each one of your data point, the features might not be binary features. Instead of that, they might take 4 values or 6 values, right? So now you cannot express it in the form of a Bernoulli distribution. You have to use a multi-Bernoulli distribution. But the general recipe would still be the same. As long as you can compute this P, you can then use it, right? The same thing could happen even for the class. So the class here takes 2 values, but if it takes 3 values or 6 values, then you can use a different distribution and still compute. So that is that. So these are the general expressions, and if you look at sort of the slides, these are more nicely written out. So when you try to do the previous problem, all you need to do is follow this recipe, right? So these are the MLE estimates, where this is the MLE estimate for the class. And as I said, this is basically how many times you see that class in the training data divided by the total size of the data. And the same thing, the probability of each class conditional feature is this. So how many times you see that feature to occur for that class divided by total number. So let's look at an example and then that will be more clear, right? Let's do the example first. Alright, so let's go here. So let's say you have a simple example where you're trying to predict let's say your training data looks like this, right? So you have 3 features. So this one is x1, x2, x3. Let's say let's make 4 binary features, and then we have a 1, which is our class, right? And let's say these are just the values that we take. I'm just going to write it out at this page. So let's say this is some data that we have, training data. So that each example is represented using 4 binary features. And then the class, of course, is binary as well, right? And what we need to do now is we need to learn our line-based the parameters for a line-based classifier so that we can say what is, and then the question will be that I want to find what is the probability of this vector 1 0 1 1. So, the probability of 1 1 1 1 right, so this is what we want to compute. What is this probability, right? So of course I became a little careless with my notation, but this in probabilistic terms, what we want to compute, what is the probability of y equals to y1, y equal to 1 given x1 equal to 1, comma x2 equal to 1, x3 equal to 1, x4 equal to 1. This is our test example, and we want to find the posterior probability for y, right? So let's see how we can do that using 9 things. Okay, so remember what we want to compute is what is the, so this can be written as using Bayes classification sort of the expression, or sorry, Bayes rule, is what is the probability of x1 to be 1, x3 to be 1, given y is 1, times probability y is 1, right? And divided by the same thing, given y is 1, and the other side. Given y is 0, times probability y is 0. Right? And now what Bayes classification tells you is that this is nothing but the theta, right? So this theta is essentially number of times you see 1 in the whole data set. So we just count that. So we saw 4, 5 out of 8. So theta is actually 5 by 8. It's the number of ones we saw in the whole data set, right? So let's keep it aside for later. Now what we want to compute it is for each class. So let's say let's just compute all the theta. So this is for y equal to, let's say, 0, right? So we need to compute what is theta 0, 1, which is what is the probability associated with the variable that is x1 given y is 0, that will be, right? So this one will be, you just count in the 0 rows. So when y was 0, so this, and this, how many times did I see x1 to be 1? So 1, only once, right? So it will be 1 by 3. So this is where you have to be very careful. So what we are trying to compute is, we are just using that that formula. We're just computing those things, those expressions, right? So we're just computing these expressions. What is the parameter associated with each class and each attribute within that class? So let's do that here. So what I said was that for class 0, for the first attribute, it is 1 by 3, because for all the training examples in which y was 0, I saw 1 time x1 to be 1 out of 3 times. Yes?
Sorry, where did that theta equals from the base come from?
So, up here?
Yeah.
Okay. So this is the probability, this is the variable which is class variable, right? So this is, as you remember, in the slides, I wrote it as theta will be nc over n. How many times you saw class 1 in 1? After all of your training examples. So what you do there is you just see how many times did you see 1 out of these 8 examples. So this is 5 by 8. Right? So this will be, then we need to compute for the class 0 for the second variable for this part. So this will again be the same process. So for all the 0 rows, right, all the examples that were 0, let's see what did x2 take. How many times x2 was 1? So it was 1 once, right? So it will be 1 by 3 again. And the same thing for the third attribute, it will be 1 once. And for the fourth attribute was 1 once again. Then, so these are the probabilities, these are the parameters that we estimated for the first class for each beta, right? And the same thing you will do here is y equal to 1, theta 1, 1 will be. So then now you look at these ones where y is 1. And then you essentially count how many times you see 1 in the first attribute. So we see 3 out of 5. Right? And theta 1, 2 will be 3 out of 5. Looks like very hastily covered exam. 1, 2 out of 5. And then here, 4 out of 5. Right? So now you have all these parameters. So now, essentially, you have trained your model. So now you know everything that you need to know to compute these values. All right? Any questions so far? So it's a little involved process. So you'll get a couple of questions in the exam, and of course in the variance quiz as well. And it's very easy to make mistakes here. It's just sort of counting things, right? Of course, if you implement it, it's easier. It's less likely that you'll make a mistake or the computer will make a mistake. But as humans, you have to be very careful about all of these counts. Right? So now, once we have trained the model, we need to use it to compute this probability. For a test example, what is the probability that y will be 1, right? So for that, what we do is we need to compute all of these values, right? So let's first compute the top of that. First compute what is p x1 equal to 1, x2 equal to 1, given y is 1, right? Now, because of Naive example assumption, we can write it as product of x1 equal to 1 given y equals 1, x2 equal to 1, y equals 1, and x3 equal to 1. Right? Now we make use of these entries here, our trained model. Now this is what is the probability that the first feature takes the value 1 when your class is 1, right? So that will be given by theta 1, 1, because that is sort of representing that value. So that will be theta 1 times this will be theta 2, 1 times theta 3, 1 times theta 4. Alright? Just as a side note, let's say if we had x2 equal to 0 here, right? Then instead of x theta 2, 1, we would have put 1 minus theta 2, 1. So that is the probability of x2 to be 0 given y, right? Right here. P, so of course P x2 to be 1, y equal to 1 is theta 2, 1. But P x2 to be 0 given y is 1 will be 1 minus theta 2, because this is just the other probability, right? It takes two values, 1 is 0, 1 is theta 2, 1, 0 is 1 minus theta 2, right? So that is the idea. So now you can compute this one. The same way, and of course, we also need for the denominator, we want the same value for the y equal to 0, right? So p x1 equal to 1, x2 equal to 1, x3 equal to 1, x4 equal to 1, given y equal to 0 will just be the same thing. Now, but in this case, we will use the thetas for the 0th class. So 0, 1 times theta 0, 2, theta 0, 3. Alright? And this will give you that, right? And now you already have this quantity, and this quantity. Okay? And then of course Py equal to 1 is just theta. Right? And Py equal to 0 is 1 minus theta. And now you just substitute it. You don't do that math, but theta of course is 5 by 8. 1 minus theta is 3 by 8. Right? So these two values we don't know. We also know each one of these values as well. You just multiply that, put it in this formula over here, and then you get the probability of the whole thing.
How long does this actually perform?
How well does this perform? So, of course, we are making a very simplifying assumption here that all the features are independent of each other, right? If that assumption is true, it works very well, because after that, there's nothing else in this world, right? And of course, if you have enough data, sure, right? So in practice, I've seen it works fairly well, even though it's making very simplifying assumptions. But in practice, what happens is that when you have data, I mean, in the modern world, it's easy to get a lot of data. So availability of data for training is relatively easy. So that problem is not there that much. The issue of independence, often what I have seen is that it does not affect real applications that much. I mean, it tends to do reasonably well. People use this more as a baseline. Like, let's say you come up with a new model. What people do is they say, okay, here's my new model. Here is how my base works on this data, and here is how my model works on this data. So you need to show that it's at least better than this very simple algorithm. So it might not be used that much for in a real field setting where they would use this for making real-time decisions, but it is used to make like comparisons of how good a new model is with respect to this. But like if you want to sort of start with at some point, then 9 days might be a good start. It does not make too many, besides the independence assumption does not make too many assumptions. And in many cases, and we will see that later on, is that even if your data, even if you cannot make assumption that your individual features are independent, you can do some pre-processing to ensure independence by changing the data a little bit. So yeah, it's a decent algorithm. All right. Any questions about how the whole thing works? It's a very involved process, I know. But if you get a problem like this, right, you can solve it. The best strategy is to first figure out what all these data are. Right. Once you have all these data, then computing the posterior for a new data point becomes fairly easy. You just need to apply Bayes' rule, and inside the Bayes' rule, each one of these probabilities comes from this data. Right? So it should be the only place where I've seen students making mistakes is just in the counting part. It becomes a little tedious. Right? So instead of 4, if I had 8 features, it becomes much more tedious. Okay, one extension that I want to quickly talk about is, what if my attributes take more than one or more than 2 values, right? So let's say x4 here, right? Let's say x4 took 3 values, 0, 1, 2, right? You don't have to change things too much. The only thing that will change is that now you will have 3 probabilities. You will have probability of x4 to be 0, 1, and 2. Right? Earlier we were just computing what is the probability of x4 to be 1 given the class, and then we were assuming that the probability of x4 to be 0 is just 1 minus of that. Right? But if it takes 3 values, then you explicitly figure out what is the 3 probabilities. So essentially what you're doing inside is that you are assuming that this variable, because it takes 3 values, we are going to express it or model it as a multi-unity aggregate, which means that it can take 3 possible values. That means you need 3 probabilities. Probability of it to be 1, 0, 1, or 2. Right? So the math still sort of holds. The only thing is that you need to compute more data instead of just 1 per class. So that's the only difference. But otherwise, the whole thing will still be same. So if x4, right, for example, takes 3 values, zero, 1, 2, then the only thing that will change, because everything else will still be the same, the data is still binary, all of the other features are still binary. Only thing that will change is that you will compute theta 0. So you'll actually compute theta 0 to 0, theta 0 to 1, and theta 0 to 2, which means probability for second feature to be 0, 1 or 2 given this class, and then the same thing you compute for the second class, theta 2, 0, theta 1. Right? So it will just become a little more involved, and more numbers to sort of take it. But the process is still the same. You're still counting, right? So naive-Bayes classifier and many classifiers that deal with discrete data are primarily just counting. They're just counting from the training data. There is no very explicit gradient descent happening like we did in neural networks. But internally, it did maximize the likelihood. So you did the same process. There was some objective function that you maximized. But it turns out, because the data is so simple, is that the expressions are fairly straightforward. Right? Any questions so far? Great. One thing that you can do beyond that, if you remember our discussion from last week, is that, remember that notion of black swan paradox, right? What if some values are not observed at all, right? Let's say in our example, let's say here, right? Let's say instead of 1, this was 0, right? Now, when you compute theta 0, 1 or theta 0, 4, so what you'll do is you look at all the 0 training examples and then see how many times did you see a 1 here. And it turns out that you saw it none. You saw it 0 times, right? Which means that your theta 0, 4 will be 0. Now suddenly what will happen is, because this probability is 0, when you compute these values, it will make everything 0, right? And suddenly you'll get very strange numbers. And that is the issue of the black swan paradox, is that since you have never seen it in training data, there is no reason for you to put anything besides 0 there, right? So the way to tackle that, of course, if you remember, is by incorporating a prior, right? So the prior is easy to incorporate as well, because if you remember, each one of these variables is a node kind of variable, which means that you can add a beta prior. So you can add a beta prior to your class, the theta for the class, right? And you can, this is something that you'll have to add, of course. And then you can also add a prior for each, within a class for every feature. And that can also be something else, right? So there we can go nuts, right? You can have a different prior for every different variable for every class, or you can take the same prior, right? And what will happen then is that whatever you compute in your theta, you can adjust it by adding the prior. And if you remember, the posterior for each parameter will also be a beta distribution, because they are conjugate to each other, and they will look like this, right? And then what you do is, then one thing you can do is you can say, let me take the map estimate, the maximum of posteriori estimate from this posterior, which will just be n1 plus a0 minus 1 over the whole sum minus 2, and then use that, right? So the only thing that will change is that instead of doing n1 over n, which you did here for class 1, it will be n1 plus a minus 1 over whatever, right? So it will be a simple adjustment, but the benefit of that will be that even if you might not have seen some value, so you would be able to handle the black swan paradox. So even if you had never seen some value, you will not have a 0 there. You will have something, right? And then of course, if you are braver, then you can say that I am not going to use just one estimate, the map estimate. I'm going to use every possibility, and then multiply it with its probability. That's the Bayesian average, right? And then you can do this whole thing. And it turns out, because they have such simple expressions, relatively speaking, even the values that you will get for Bayesian averaging will also be some numbers that you can compute. So this will just be like this, right? Slightly different, but similar idea. All right. So last time I had it. Okay. So of course, I already went through the example for each day, but you can also use this data set for your example as well. So let's look at it quickly. So maybe when you get back, you can look at it. So the idea is the same. You have three features, right? They're all binary, and there's a class which is binary, right? And now you want to compute what is the probability of a new example to be malignant or benign, right? So what is P Y to be malignant given X is this, right? And you can do it in the same class that I showed you earlier, right? So you can compute what is the class conditional estimates for each feature by just counting, right? So let's quickly do it. So what will be Py equal to malignant? That is a theta, right? So all you do is you count how many times you see malignant characters. 1, 2, 3, 4, 5. That's 5 over 10. So it's half. And the other thing also will be half. Then what is the probability of x1 to be circular given y is malignant? That will be your theta 1 comma 1. So there what you do is you look at each malignant rows, 5 of them, see how many times you see circle. 2, 3, right? So 3 by 5. And so you repeat the whole process. Now here, you need to be slightly careful, is that there is no notion of 0 or 1 here, right? So which one do we take as 0, which one do we take as 1? It's arbitrary, as long as you use the same notation throughout, right? So you can initially assume that I'm going to treat circular as 1 and the other one as 0. So what you would compute, the theta, would be probability of it to be circular, and then the probability of it to be oval will be 1 minus 1. Alright, so try out this example as well as a couple of examples in the practice quiz, and I have one in ingredients as well, and that should set you up. Any questions so far? Alright, so, and of course, I made this course yesterday. So in last year's class, I went through this example as well. So if you go to Piazza, I made a post. The second video, the start of that second video is where I actually go through this whole example. So that should give you a little more clarity about this, right? So again, a reminder, the midterm is on Friday morning at 8. Try to be here at 7:45. I'll send you the instructions later as well. But please bring a picture ID, your UP card or a driver's license so that we know who you are. Come at 7:45. On the morning of the class, I will send you a seat assignment. So each one of you will get a seat to sit on. There are numbers on this seat. The class, the exam is here. You don't have to go anywhere else. So basically, you get that number, you come and sit in that seat number, and we'll give you the paper. It will be 20. Bring some rough, pages for stats work, and we will give you a bubble sheet to fill. 20 problems in 2 hours. They're all objective questions, and there's what to say. It's open book, open notes. Feel free to bring anything. All right. Any other questions? Cool. Thank you very much.